Hello everyone, this is Chaitanya is from Sri Venkateshwara College of Engineering. Let us discuss on the topic eigenfunctions and eigenvalues. Introduction to eigenfunctions and eigenvalues. Eigenvalues and eigenfunctions are fundamental concepts in linear algebra, differential equations, and quantum mechanics, with significant applications in physics, engineering, and other sciences. The energy values for which Schrödinger equation can be solved are called as eigenvalues, and the corresponding wave function are called as eigenfunctions. Defining eigenfunctions and eigenvalues. An eigenvalue is a scalar that satisfies the equation AV is equals to lambda V, where A is a linear transformation and V is a vector. An eigenfunction is a non-zero function that satisfies the equation Ly is equals to lambda y, where L is a differential operator. Eigenvalues and eigenfunctions helping in finding solutions to differential equations with boundary conditions. Mathematical formula L xi is equals to lambda xi. L is a linear operator, lambda is the eigenvalue, and xi is the eigenfunction. Role of eigenfunctions in quantum mechanics. Eigenfunctions represent the stationary states of quantum system with time-independent solutions. They form a complete basis set of the Hilbert space of quantum states. A general quantum state can be expressed as a linear combination of eigenfunctions. Role of eigenvalues in quantum mechanics. Eigenvalues determine the possible outcomes of measurements in quantum systems. When a measurement is made, the system collapses into one of its eigenstates. Then, the probability of obtaining a particular eigenvalue is given by the square of the amplitude of the corresponding eigenfunction. Taking as an example, application of Schrödinger wave equation, a particle inside a potential well of infinite height. Let us consider a particle of mass m inside a potential well of width a moving along x direction. The potential inside the box can be considered as 0 and outside the well it is considered as infinity. Inside the well v is equals to 0. The Schrödinger wave equation can be written as d square xi by dx square plus 8 pi square m by h square into e of psi is equals to 0. That is taken as first equation. D square xi by dx square is equals to minus 8 pi square m by h square of e into xi. Then it is written as minus h square by 8 pi square m d square xi by dx square is equals to e xi. H xi is equals to e xi. Let 8 pi square m by h square e is equals to k square. That is equation number 2. Thus equation 1 can be written as d square xi by dx square plus k square xi is equals to 0. Question number 3. The general solution of the above solution can be written as xi is equals to c cos of kx plus d k of d sine of kx. It is equation number 4. Applying the boundary conditions to the equation 4. Using these boundary conditions in the solution of wave function can be written as 0 is equals to c cos 0 plus d sine 0 at x is equals to 0, xi is equals to 0. Then c is equals to 0. Therefore, xi is equals to d sine of kx. It is equation number 5. 0 is equals to d sine of ka at x is equals to a and xi is equals to 0. Since c is equals to 0, d sine of ka is equals to 0. Therefore, xi is equals to d of n by pi a into x. It is taken as equation number 6. Substituting the k value in equation 2, we get 8 pi square m by h square e is equals to n square pi square by a square. E is equals to n square h square by 8 ma square, where n is equals to 1 represents the ground state and ground state energy or 0 point energy. Then E naught is equals to h square by 8 ma square, where n is equals to 2 represents first excited state and first excited state energy. E1 is equals to 4 pi square 4h square by 8 ma square is equals to 4 E naught. N is equals to 3 represents second excited state and second excited state energy, where E2 is equals to n 9h square by 8ma square is equals to 9e naught. By normalization process, we can write as minus infinity to plus infinity d square sine square n pi by a into x dx is equals to 1. We know that using sine square theta formula, sine square theta is equals to 1 minus cos 2 theta by 2. Cos 2 theta by 2, then we get after integration we get d square of a by 2 is equals to 1. Then d is equals to root 2 by a, then xi n is equals to root 2 by a sine of n pi by a into x. This is 7th equation and final equation. Then eigen functions, probability densities and eigen values. The energy eigenvalue of a particle in a potential well of height is given as E is equals to n square h square by 8ma square. The eigenfunction is n is equals to root 2 by a sine of n pi by a into x. The probability of location and energy values varies in various allowed energy levels as given below. Then as shown in the figure 1, then n is equals to 2 as shown in the figure 2. Properties of eigenfunctions and eigenvalues. Completeness, orthogonality, normalization. Completeness, any wave function can be expressed as a linear combination of eigenfunctions. Orthogonality, eigenfunctions corresponding to distinct eigenvalues are orthogonal to each other. Normalization, eigenfunctions are normalized to that the probability of finding a particle within the entire space is 1. Thank you.